Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firdaus, and today I'm going to present my research proposal titled The Comprehensive Quality Control of 68 Gallium Chloride, an intermediate product of gallium-68 based radiopharmaceutical produced by a General Electric PETCT Secatron using liquid target. My supervisor is Dr. Intan Diana from ESPER. A little bit introduction for my research proposal is that nowadays cancer is the most common disease not only in Malaysia but also globally. Statistic from WHO in year 2020 shows that approximately about 14,800 new cancer cases were reported, and the risk of developing cancer before the age of 75 years old is about 14.8%. That's quite high actually. And the cancer is a leading cause of death worldwide. In Malaysia alone, it's about 29,000 of deaths that were caused by the cancer were reported. Actually, there are many types of cancer. As you can see here, for males, the most common one are lung, colorectal, prostate, nasopharynx, liver, and for female is breast, colorectal, ovary, cervix, and corpus cancer. So how clinicians and physicians characterize or diagnose the cancer? Okay, one of the modality that clinicians use to diagnose and characterize the cancer is using a positron emission tomography and computed tomography, or in short we call it as a PETCT scanner. This is one of the example of PETCT scanner that produced by GE Healthcare. So how it works? For CT scan, we can able to detect the organ and bones, and for PET scan, we can able to scan the cell activities, and they combine this image together to give a 3D imaging that where we can know where exactly the location of high cell activities that caused by the cancers. And of course, this PET scan cannot operate without a tracer. So the tracer can either be produced using a medical cyclotron or a generator. And one of the most widely used tracer for PETCT scanner is fluorine 18, which is labeled with fluorodeoxyglucose. And fluorine 18 is produced by the medical cyclotron, and it is considered as molecule of century because it is most widely used and very good tracer for most type of the cancer. But not all cancer can be detected by using a fluorine 18. There are other tracers that can produce better imaging. For example, here is a copper 64, carbon 11, iodine 124, and also a gallium 68. And today we are going to focus on gallium 68 because it has a very high potential to be a very good tracer and has better imaging for neuroendocrine tumor compared with fluorine 18. And it also has a huge demand in theranostic application, where the same peptide here, dotatate, either can be labeled with 68 gallium to use as a diagnosis tracer, and the same molecule, the same peptide, dotatate, can be labeled with 177 lutetium and can be used as a therapeutic agent to cure the neuroendocrine tumor. So like I mentioned just now, the tracer can be either produced by a medical cyclotron or a generator. And for gallium-68, the conventional way is using a germanium-68 generator. The germanium-68 is the mother, which has a very long half-life. Which is about 270.95 days, and when it decays, it produces the 68 gallium, which has a very short half-life, which is 68 minutes. And when the gallium decay, it produces the zinc 68, which is non-radioactive solutions. So the generator itself is very expensive, and it has a very huge demand. We actually need to pre-order the generator 2 or 3 months before we actually can get to use it. And there is no company in Malaysia that produce the generator. We actually have to order from outside of the Malaysia to get the generator. So the generator is it has very limited resource, and it takes about 4 hours to reach maximum yield after the last elution of the generator, which means that if we want to produce multiple batches of gallium chloride, we actually have to wait about 4 hours in between to produce next batches of gallium chloride. And every generator, we can actually produce about 0.6 to 0.9 gigabecquerel or 15 to 25 millicurie, which is enough for 2 or 3 patients. And this is one of the typical cross-section of the generator, where it has a column that we put the germanium-68 inside, and it was shielded by a LED. It's very easy to use and very straightforward. We just need hydrochloric acid as eluent to elute the gallium and produce the gallium chloride from the column. The gallium chloride may contain measurable activity of long-lived germanium, which is the mother. And in order for us to detect whether it has the mother or not, we just do the breakthrough test. So another alternative method to produce gallium chloride is using medical cyclotron. Actually, this is a very new method, and in Malaysia there is no other facility that can produce gallium chloride using medical cyclotron. In year 2020, Institute Cancer Negara has upgraded its facility that includes the target for the gallium chloride production and also its synthesis module that can produce radiopharmaceutical gallium chloride base. So how cyclotron works? Actually, the cyclotron is quite complicated if compared with the gallium generator. Cyclotron is a device by which a positively charged particle can be accelerated and the desired nuclear reaction can take place. A positively charged particle can be accelerated to a high energy with the help of oscillating electric field by making it cross the same electric field again and again with the use of strong magnetic field. So the next question is, why we want to use cyclotron instead of gallium generator, and how safe it is for clinical use? The reason why we want to use cyclotron is we want to sustain and expand the production of the gallium chloride. As we all know that the production of gallium chloride in using a gallium generator is very limited, and by using the by using the medical cyclotron, we can actually expand the production of the gallium chloride. And we also want to produce gallium chloride for research purpose to make it and produce another gallium chloride 68 based radiopharmaceutical. And in future we would like to commercialize the gallium chloride to other nearby facilities in Institute Cancer Negara. And how safe it is for clinical use is going to be our main objective for this research. As we all know that the production of gallium chloride using gallium cyclotron is very complicated compared to a generator. It needs a suitable condition for irradiation to maximize the production yield of the gallium chloride and minimize the production of impurities. Short and long-lived non-isotopic impurities may get produced along with the gallium chloride. For example, 13 nitrogen, 11 carbon, fluorine 18, and copper and cobalt isotopes and other radiometals. It may produce 66 gallium or 67 gallium, which is impurities that we don't want in our final product. So here are some of the literature's review that related to gallium chloride production using cyclotron. The production yield was found to be as high as 1.93 plus minus 0.11 gigabecquerel, and production takes about 2 hours. Impurities such as metal that include zinc and iron, significant production of isotopic impurities such as gallium 66 and gallium 67 during the bombardment process, and chemical impurity may present in the product solutions. Impurities such as metal will compete with gallium 3+ in the complex section with different chelators, which negatively affect the radio labeling yields. So these are the main objective of our research. The first one is we want to determine whether the intermediate product is safe for clinical use, for our research and for routine productions. And we want to synthesize an intermediate product of gallium 68 based radiopharmaceutical using cyclotron. And we want to quantify the percentage yield of labeling in the intermediate product, and we want to quantify the metal, the radiometal and chemical impurities in the final product. So these are some of the methodologies that we are going to use for this research. The irradiation of precursor target material using an electron accelerator and measuring the production yield of the final product. The analytical method for chemical separation using TLC to quantify the percentage of labelings, and qualitative and quantification of impurities using various instruments such as AAS for metal impurities, dose calibrator for half-life calculations, a gamma ray spectroscopy to check the radionuclidic purity, and gas chromatography for solvent residual. And this is the expected result for this research. The source is from the IAEA for gallium 68 cyclotron productions. The acceptance criteria for the pH is between 4 to 8. The radionuclidic purity is between 62 to 74 minutes for gallium 68, and the radiochemical purity checking using HPLC or TLC is more than 91% of labeling, and residual HEPAS we can check using TLC is less than 0.2 milligram per 10 milliliter. And metal impurities for zinc and iron is less than 10 microgram per gigabecquerel, and the residual acetone check using GC is less than 50 milligram per 10 ml. Okay, that's all from me. Thank you.